Welcome back to my channel again. In this video I will talk about understanding operating system and scheduling. How the OS decide what runs, when and for how long. The invisible logic behind every smooth digital experience. The conductor of the digital orchestra. The core problem. Modern CPUs execute one line instruction at a time per core, yet dozens of processes compute for attention simultaneously. The solution, the OS scheduler, acts as a gatekeeper deciding which process uses the CPU, when, and for how long. Why it matters directly determines system responsiveness, throughput, and fairness across all running processes. The three levels of scheduling: long term scheduler, administration control, decides when new process enter the ready pool, control the degree of multi-programming. Medium term scheduler, swapping moves processes in out of memory to balance multi-programming levels and optimize memory use. Short term scheduler, CPU dispatcher, the most frequent scheduler, selects the next ready process in milliseconds and microseconds. Scheduling criteria, the goal of the game. Throughout, throughput, maximize work completed per unit time. Wait time, minimize time spent in the ready queue. Response time, ensure quick feedback for interactive system. Fairness, give every process a fair share of the CPU time. Deadlines, criteria for the real system like robotics. These goals often conflict. Maximizing throughput may hurt response time. Scheduling requires careful trade-offs. Key scheduling algorithms: first come first serve (FCFS), non-primitive runs, processes in arrival order, simple but long job can block short ones. Conway effect: shortest job next. Non-primitive picks the smallest CPU burst next, optimal for wait time, but risk starvation for long jobs. Round robin: primitive, each process gets a fixed time quantum, fairness and responsive time. The standard for the time sharing. Priority scheduler: higher priority processes run first, flexible but low priority process may stray without engaging mechanism. Advanced algorithm and real world implementation. Multi level queue, processes specific queue with distinct algorithm. Multi level feedback queue, processes move between queues dynamically, prevents stagnation. Linux CFX completely fair scheduler, assign virtual runtime to ensure fair, share and low latency. Multi-level queue divides the ready queue into separate tiers, foreground versus background, each with its scheduling policy. MLFQ, processes migrate between queues based on behavior, CPU bound processing, IO bound on one's rise, prevent starvation. Linux CFX uses virtual runtime to track CPU entitlement, targeting 6 ms latency and a near perfect fairness. Multiprocessor scheduling, harnessing parallel power. When multiple CPU cores are available, the scheduler jobs become both more powerful and more complex. The challenge of parallelism, asymmetric multiprocessing. One master CPU handles all scheduling, uh, others execute tasks simple, but the master becomes the bottleneck. Symmetric multiprocessing, each CPU has its own scheduler or shares one better long balancing and scalability, the modern standard. Processor efficiency, keep a process on the same CPU, the leverage, warm, cache. reducing memory access latency. Measuring performance. How do we know it's working? Total time from processing process arrival to completion. Waiting time. Total time a process is spent idle in the ready queue before getting CPU. Response time. Time from request submission to first output criteria for interactive system. Through throughput, number of processes completed per unit time, a measure of overall system productivity. CPU utilization, percentage of the CPU and CPU is actively busy, ideally close at 200%. The scheduler, using unsung hero, from managing your instant messages to running complex simulation. The OS scheduler is the invisible force ensuring your computer runs smoothly and efficiently. Orchard, every process completing for CPU time. Optimize this throughput, fairness, and responsiveness. Adapts to single core, multi core,